Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we will start a new topic, somehow related to the simple harmonic oscillation, but till now we have discussed simple harmonic oscillation without any external effect, for example, no energy pumping, no energy dissipation. Then we discussed the simple harmonic oscillation in the presence of an energy pump, or what we called a forcing term. So, we actually specially discussed the case of a periodic force, and then today we will discuss a more realistic case where we will also take the viscosity or the dissipative nature or the drag of the medium in which the oscillator is moving into account. So, this thing is much more realistic, because you just think that whenever we are talking of a model when a spring is moving, the one point of the spring is actually attached to a rigid support and the spring is moving. So, this does not in general move in vacuum, right, although we think for the ideal case it is vacuum, but it is always move in a viscous medium, either let us say in air or in water, or you can think of some fluid for making some interesting problems. But in all cases the medium will have some viscous effects. The medium will give some friction type of force in order to oppose the motion of the oscillator. Okay. So, these things are actually, if you really think a little bit carefully, they do not come in a puristic way of thinking, they do not come in the realm of classical mechanics, rather they are the part of thermodynamics, as you can learn afterwards. Okay. But in classical mechanics, somehow at some point we have to model some viscous force, and in the first week's lecture when we were just talking of different type of force and Newton's law, we said that in general a very well known force model to model a viscous drag is a force which is directly proportional to the velocity, because if you have such a force you can directly show that the total mechanical energy of a system is actually decreasing with time, or actually you can take the coefficient of the drag force in such a way, sometimes it can also increase, but that is immaterial in this case. The main issue is that you can show that a force which is proportional to, so if you just remember this thing, that if your force is equal to some, let us say, I do not know, some alpha v, okay, and then you simply say that m r double dot is equal to alpha. So, v is r dot. Okay. So, then you can always say that okay, I can actually just, so here I do not have any other potential force or any other conservative force field, just one force field, and we are simply saying that if I just do m r dot r double dot, and here it will be alpha r dot vector r dot whole square, and that gives me actually half d dt of, or I can write like this, d dt of half m r dot square, that will be equal to alpha r dot whole square. Now, if I choose alpha to be less than 0, then this thing will be always less than 0, and so it actually guarantees that the total kinetic energy of your system decreases. In the same way, you can actually think that okay, let us say the particle is moving under the influence of a influence of a conservative force field like this, is equal to minus gradient of phi plus another force field which is like this. Okay. Then you can actually also show, just by doing the dot product with r dot, you can actually show that d dt of half m r dot square plus phi will be equal to alpha r dot square, and again if alpha is negative, then it is actually negative. So, you can also say that here the total mechanical energy is also dissipating. Okay. So, this is actually a very popular model for dissipative force, and Stokes, he said that this is actually a very useful model which you can also verify in everyday experiments if the particle which is moving in a viscous medium does not have a very high speed. So, if the particle is moving with a relative velocity with respect to the viscous medium and the relative velocity is moderate enough, then the resulting dissipative force can be modeled to be proportional to V. However, if the particle is moving with a higher speed and some turbulent effect are coming into play, then just a force which is proportional to V does not work very well, and then you have to think of some a force whose magnitude is proportional to V to the n, and most popularly we use V square model. This is also a good exercise for you guys to try that how the solution changes and how this energy conservation gets affected if you have, let us say, a particle which is moving under a conservative force field and a force field which is, let us say, having a magnitude like beta V square, where beta is negative. Okay. Now, coming back to our original discussion. So, here whenever we are talking of a simple harmonic oscillator. So, simply if you remember that in general there is just we are talking about 1D simple harmonic oscillator, and this is the equation of motion for that. And then of course, if you say that if I have a forcing term, then what we wrote yesterday was this. Okay. And so, this is with forcing, and finally, if you want a drag force, then what you can do, this times some plus omega square x. Okay. I am now just considering no forcing which can pump energy, but some dissipative effect. So, I can write with some minus 2 lambda x dot. Okay. This is a forcing whose coefficient. So, lambda I am just considering to be lambda is greater than 0 here, and this minus is just to ensure the dissipation of energy, and x dot is the velocity. So, that I can write. Why this 2 factor comes? This is just for some sake of calculations convenience. There is no other intrinsic physical reason for that. Okay. If you write this, then you can actually write the resulting equation, which is x double dot plus 2 lambda x dot plus omega square x is equal to 0. So, this is the fundamental equation of dynamics for a particle which is oscillating, but undergoing a dissipative effect due to this force. Okay. Now, you see that before doing anything, we will first classify the nature of the differential equation, which is given by this. So, once again, this equation is a second order. Okay. This is linear because you see x double dot x all are linear in x. So, linear ordinary differential equation. Now, it is homogeneous or non-homogeneous. So, it is homogeneous because all the x and its derivatives are set aside, and on the other side you just have 0. So, it is second order linear ODE. So, I can write like this: homogeneous ODE. Okay. With constant coefficients. That is something also very interesting. Okay. This is constant coefficients. 2 lambda you know, and that you know because you know the medium. So, this coefficient we sometimes called the damping coefficient, but in some books you will also see if I write this as 2 lambda, then lambda is called the damping coefficient. So, this is exactly the half of the coefficient which you write in front of the dissipative term in the dynamics equation of dynamics. Okay. So, this is the damping coefficient. Okay. I will just use this convention so that you are not confused while going through some other textbooks. Now, what is the solution for such a equation? Okay. So, I am just writing the equation is once again x double dot plus 2 lambda x dot plus omega 0 square x is equal to 0. So, this is a homogeneous equation. So, there is no question of complementary function and particular integral. The complementary function itself will constitute the total solution, of course, as you can understand, but we have to now find that. So, whenever you have a like nth order linear ordinary differential equation with constant coefficients, okay, a very useful trial solution is that if you take x is proportional to some e to the power some quantity, let us say r t. Okay. Now, of course, the first choice you can think from your knowledge of undamped normal free simple harmonic oscillation that this r can be simply I omega. So, the first question is, can r be equal to I omega? Okay. So, if you do that, so that means can x be equal to some a e to the power I omega t, or I just make sure that I have just put, sorry, shouldn't I just write something. Okay. Let me just give a clarification over here. So, up to this I just wrote omega. Okay. So, whenever we are talking the case of damped oscillator, it is always good to write this omega 0 square this omega square as omega 0 square. Okay. So, I then just call that omega 0 is the natural frequency. Why I am now distinguishing this omega 0, if you just remember this coefficient lambda. So, you see that lambda times x dot, that means x by t, dimensionally I am just talking in terms of dimension, dimensionally this is of the homogeneous to omega 0 square x, and omega has a dimension of 1 by t square, 1 by t square times x, and then you actually can say, and so that is lambda will also have a dimension of 1 by t, which is a dimension of omega 0 as well. So, you see that there is another frequency like variable constant comes into play. Okay. A frequency like quantity, which is a constant of course for our case, comes into play. Okay. It may or may not be constant, but for the sake of simplicity we just for the time being we assume this to be constant, and then we just denote this omega as omega 0. So, omega 0 is the natural frequency and lambda is another frequency coming out of the dissipative effect. Okay. And then the question is, can r is equal to I omega 0 or a to the power I omega 0 t. If you do that, of course, you will see that these two terms will vanish and this term will not vanish, because if you just put this solution here, you will find this will give you simply minus omega 0 square x plus 2 lambda I omega 0 x plus omega 0 square x is equal to 0. If I have not made any mistake, just a minute. So, dx dt, yeah. So, it will give me I omega 0 here over, of course, and then there should be this thing. So, it is x, yeah, and then these two will go away, finally giving you 2 lambda I omega 0 x is equal to 0. So, lambda omega 0 they cannot be 0 in general. So, x must be 0. So, this is giving me an absurd case, okay, absurd case, and that is why I cannot take this type of solution, no. So, what to do? I will just make this as general and I will just think, I will just search that, or I will just check what happens. Okay. So, if I just make this, then of course, my x dot becomes, so I can write more precisely that my x will be some, I do not know, like some e to the r t, and then if x, yeah, and x dot is equal to a r e to the r t, and then finally you write x double dot, which is equal to no, just a minute, yes, that is true, r square e to the r t. So, that you can always write as r times x, here you can write r square times x. So, putting this in the main equation of dynamics, we get r square plus 2 lambda r plus omega 0 square is equal to 0. So, you see you will get a quadratic equation in R. Okay. I just left R as free as possible, so that I could not put any constraint on R a priori. Okay. And if you now just solve that, you will see this is simply, so R will be now equal to, so minus b plus minus b square minus 4ac by 2a. So, minus b, so minus 2 lambda plus minus root b square, so 4 lambda square minus 4 omega 0 square by 2, which will simply give us minus lambda plus minus root over lambda square minus omega 0 square. Okay. So, that is quite fantastic that you can have two solutions like that, and you actually say, okay, then if I now say, okay, that I just have an equation which is x, then x will simply be some a times e to the power minus lambda plus root over lambda square minus omega 0 square times t plus b, I mean I cannot write like this because a is already used here, I write e1 and e2 e to the power that is true minus lambda minus root over lambda square minus omega 0 square times t. Okay. So, you see that I will simply now take x like this. Okay. Now, here there is, we have to just understand one point, we have to be very careful that here we are just making x real or imaginary or in general complex, and that is also, that is according to our freedom, we have to be careful in the formation of the equation, of course. So, you can actually, what you can do, that you can simply see that when lambda is greater than, so in this equation, so when lambda is greater than omega 0, then there is no problem, both these solutions are, both the r, okay, the values of r are real. Okay. But if lambda is less than omega 0, then they are not real, this part is imaginary, and this the roots of r will be then complex in general. So, if you want to avoid this mathematically from the very beginning, you just have to do something once again, that you have to cast the whole problem in terms of a complex differential equation with the same coefficients. Let us say, so z double dot plus 2 lambda z dot plus omega 0 square z is equal to 0, and you claim x is equal to simply my real of z. Okay. So, I am simply writing, let us say if you now have this and you know that your z is equal to some c1 times e to the power minus lambda plus root over lambda square minus omega 0 square times t plus c2 e to the power minus lambda minus root over lambda square minus omega 0 square times t. If you know this to be true, then I can make several cases. So, case 1 is when lambda is less than omega 0. Okay. That means this thing is imaginary. Okay. So, lambda square, that means lambda square will be less than omega 0 square. If you have this, then the best way to write z is equal to c1 e to the minus lambda plus I root over omega 0 square minus lambda square. This part is of course real according to our condition, plus C2 e to the power minus lambda minus I root over omega 0 square minus lambda square t. Okay. Now, I can actually, since z is complex, I can also think they can be complex in general. Okay. And if they are, I can just call omega root over omega 0 square minus lambda square as omega d. I can actually write this is equal to C1 e to the minus lambda plus I omega dt plus C2 e to the minus lambda minus I omega d t. Okay. Now, finally, x will be real of z, and then you can actually say this is nothing but half z plus z transpose, sorry, z plus z conjugate, sorry, z plus z conjugate, and if you do carefully, it will simply give you half C1 plus C2 bar, or just conjugate, bar should be confusing, yeah, conjugate, okay, e to the minus lambda plus I omega d t, okay, plus C1 conjugate plus C2 e to the minus lambda minus I omega d t. Okay. Now, if you do this thing again carefully, you will see that you will have half. So, this e to the minus lambda t is actually a real quantity, it can come out e to the minus lambda t, within bracket you will have this C1 plus C2 star e to the I omega d t plus the complex conjugate of this thing. And if you just call this thing, if I just call, if C1 plus C2 star is equal to a e to the power I alpha, okay, where everything a, alpha, all are real quantities, then I can finally write, just you do this calculation and check, I can finally write this will be equal to, so there will be some e to the minus lambda t times cos omega dt plus alpha. Okay. So, what I am just suggesting you that you first write this thing and then you write this one. What will be the complex conjugate? This is nothing but C1 star plus C2 e to the minus I omega dt, and then you call C1 plus C2 star as a e to the power minus I alpha. So, what will be C1 star C2? That will simply be a e to the power minus I alpha, and if you just do the manipulation algebraic, it will come like this, as where we actually used this thing that if you have something e to the I theta plus e to the minus I theta, this will be simply be 2 cos theta. That is what we used over here. Okay. If you do, you see that this is a solution which is having a trigonometric oscillatory part, but the amplitude is no longer a constant quantity. The amplitude actually steadily decreases exponentially with time, and here this is x and this is t. So, in general, so I can say that this is exponentially decaying thing is like this, and so x can be both positive and negative, the same thing, and something like this you can actually think of like this. Okay. Yeah. So, here you see this is oscillatory but not periodic. That means, after some 2 pi period of cos function, the particle does not come to its original position because of this gradually decreasing amplitude. Okay. So, this is known as the case of underdamped oscillator. So, this is possible when your lambda is less than omega 0. Okay. That means, your medium has some viscosity, but the viscosity related frequency is less than that of the natural frequency. Then still you always have a possibility of a oscillation, but this oscillation is not a periodic oscillation. Okay. What happens when we have lambda less than or equal to omega 0? So, I just first take the case of lambda. So, first lambda greater than omega 0. Okay. Then you have your z will be equal to C1 e to the minus lambda plus root over lambda square minus omega 0 square t plus C2 e to the minus lambda minus root over lambda square minus omega 0 square t. Okay. If you remember, this one I was calling this one as omega d. So, this is omega d. Okay. So, I can also call this here omega d, or I just do not need to introduce them, this is okay. So, what I can simply tell you that here you see that we are in a case where lambda is greater than omega 0. Okay. So, this thing inside the under the root over, okay, is actually less than lambda square. So, the point is, since lambda square is greater than omega 0 square here, of course, I can write that lambda square minus omega 0 square will be less than lambda square. That is something we can always say. Yeah. And that is why you say, you see that you will have always something. So, this is minus lambda. If I just say this is something which is, so this part is less than lambda. Okay. That is what I just showed here. This is less than lambda. If you have something less than lambda over here and also here, but since lambda is with a minus sign, although there is a plus sign, the total thing will be exponentially decreasing. Here you do not have any problem because both of them are with a negative sign, and that is why they are always exponentially decreasing. What is the conclusion? The conclusion is that this z is constituted of two parts, okay. Both of them are exponentially decreasing. Okay. Now, what will be x? X will simply be e to the lambda 1 t, okay, times r e c 1 plus e to the lambda 2 t, okay, r e c 2. This is the real part of c 1 and c 2. And what is this lambda 1 and lambda 2? Because they are simply, so lambda 1 will be equal to minus lambda plus root over lambda square minus omega 0 square, and lambda 2 is equal to minus lambda minus root over lambda square minus omega 0 square. So, you see that in this second case where lambda is greater than omega 0, that means the damping coefficient actually dominates over the natural frequency, then the system even does not have any type of oscillatory motion. Okay. So, the system simply, the displacement simply decreases exponentially with time. If lambda is equal to omega 0, then this is the case of the degenerate roots, and for that if lambda is equal to omega 0, then from the theory of differential equations you can check, okay, you will have x will be equal to then r e. So, then lambda 1, of course, lambda 1 is equal to lambda 2, but your x will be simply r e c 1 plus c 2 is not the correct one, it will be c 1 plus c 2 t, okay, where actually c 1 and c 2 I can write c 1 prime and c 2 prime because they are not exactly equal to these two constants over here. Okay. So, they are two different constants. Okay. So, c 1 prime c 2 prime t e to the power minus lambda t. Okay. Once again this is equal to lambda, and that is because simply as lambda is equal to omega 0. Okay. So, that means that in this part, if lambda is equal to omega 0, this part will be minus lambda, this part will also be minus lambda. Okay. So, you will finally have a solution which looks like this. Okay. I give a name to those things. I can call this case as over damped motion, that was under damped, this is over damped motion, and this is called critically damped motion. Okay. Or critically damped oscillator, I can also write critically damped oscillator. This is over damped oscillator. So, to be very honest, in the case of an over damped oscillation and critically damped oscillation, there is no oscillation at all. Okay. The motion is aperiodic, the motion is non-oscillatory, exponentially decreasing in the first case, and the second case it will be a little bit different than a proper exponential because there is a C1 plus C1 prime plus C2 prime t times this. Now, before wrapping up this lecture, my question to you to think that between over damped and critically damped situations in which the displacement would decrease the fastest or the quickest. Okay. So, you see in this lecture we have seen the effect of dissipation where there is no forcing effect. Okay. So, in the next week we will actually see a much more realistic case where both the dissipative effects and the forcing effects are present, and they will compete with each other to have some again compromised situation. Okay. Thank you very much.